Okay, now we'll start our lecture. So basically in this multi-rate digital signal processing, we will not focus more on numerical. Basically, we will cover the basic theory of multi-rate DSP. Okay. So yesterday we have started with multi-rate DSP. So multi-rate in multi-rate DSP, we says that we can get the particular signal with the different sampling rate. Okay, so we can change the sampling rate according to the requirement. So we can, so if I want increase sampling rate, then I can use upsampler, which is a device where I can get increased sampling rate. If I want a decrease sampling rate, in that case, I can use downsampler. Okay, so we have seen the input output relation of upsampler, downsampler, how downsampling works, how upsampling works. The If I want the upsampling by factor L, then what will be the relation of input output? Okay, so in case of upsampler, there is a zero padding in the given sequence or digital system signal. Okay, so in case of downsampler, basically we will take only particular sampler, the particular signal at the if I want the downsampler with factor of 3, then I will take only of the third sampler in the third uh, value in the sequence, given sequence. And in between these, I will remove m minus 1 uh, points in the sequence. Okay, so the basic devices used in this multi-rate DSP is upsampler, downsampler. There is zero hold circuit. So both basically we will focus on the downsampler and upsampling process only. Okay, so the relation, if I say, if I want to find the sampling frequency, output sampling frequency after upsampling the signal or after downsampling the signal. So this is the relation yesterday we have seen. If I want to find the sampling frequency after this process. Okay. So in case of downsampler, it is 1 by Tm or 1 by T dash. You can say this T dash is nothing but T into M. What is M here? M is the factor by which I want the signal to be downsampled. Okay, so in case of upsampler, the output sampling frequency, input sampling frequency, we know that that is 1 by time period, this T. So that is the input sampling frequency. Output sampling frequency that in case of upsampler is 1 by T dash. Again, it is 1 by T dash, but in this case, this T dash is nothing but M by L. Okay, the T by L. Okay, so T is this input time period and L is the factor by which I want the signal to be upsampled. Okay, now there is some basic property which we will illustrate now. That is the time varying property of this sampler, upsampler and downsampler. Here I have shown only the downsampler time varying property, but in similar manner we can also prove for the upsampler. Okay, so here you can see the now we will consider that a factor of m downsampler. So I want the signal to be downsampled by factor m. So the input output relation I can write like this. So y of n is basically the output of downsampler. X of n is the input of downsampler. But we are doing downsampling by factor m. Therefore, this y of n is equal to x of n into m. Okay. So the now I will delay this input. Let us say x1 is the delayed input. So I have delayed this input sequence by n naught. Okay, therefore, xn minus n naught, I am saying this is another input, that is delayed input, which is equal to x1n. Okay, now for this delayed input, let us say output is y1n. Okay, so this y1n in I can write this y1n is nothing but x1 of m into n, right? Because of this downsampling relation. So y1n, I can say this is equal to x1 n into m. Okay, and in this case, basically what we are doing, we are delaying this sequence by n naught. Therefore, this I can write x of mn minus n naught. Okay, now the case if there is a delay in the output, like y of n minus n naught, then this is equal to x of mn minus n naught. The input output relation of the downsampler is, if this is basically if there is a delay of n naught in the output, if I'm expecting same delay in the output, so I can write my equal to n minus n naught. But I know that the relation, that is x is equal to m, in bracket I can write n minus n naught now, because this is n minus n naught here, y of n minus n naught. So if I simplify this, now this term is not equal to this y1 of n. What is y1 of n? Y1 of n is simply x1 mn, which is x of mn minus n naught. Okay, so that is when the delay output of the system is equal to the output due to delayed input. In this case, it is not the this is not the case. Means the delayed output of the system is not equal to the output due to delayed input. Okay, so in the first case, this is output due to delayed input. The second case is the delayed output. These two are not same. Therefore, I can say that the given system is time varying system. Okay, so I can say that the downsampler is a time varying system. This is linear, but this is time varying system. Okay, similar manner we can also prove for the upsampler. Okay, so upsampler is also a time varying system you will get. Okay, now the frequency domain characteristics of this upsampler. So consider the factor of 2 for upsampling the signal. The input output relation I can write like this. So xun is basically the output of upsampler, which is equal to x of n by 2. Why by 2? Because this is the factor 2 here. Therefore, this is x of n by 2, and where n will vary from 0 to plus minus L plus minus 2L like this. Here the value of L is equal to 2. Otherwise, the value will be 0. Correct? Because we are doing 0 padding there in case of upsampler. So this is the relation. Now, if I want the spectrum of this upsampler, so how I will write, this is the case illustrated for factor L equal to 2. Okay. Now, in terms of Z transform, I will write this input output relation like this. So XU of Z, so the Z transform if I apply, so this will goes like this, summation from n equal to minus infinity to infinity, XU of n, Z to the power minus n. Okay, so I know that XU of n is basically, this is only for the even terms exist, plus minus 2, plus minus 4. Okay, so therefore n equal to even is written here. This will go from minus infinity to infinity. So XU of n, I will write x of n by 2 z to the power minus n. Okay, now here I will write n by 2 equal to m. This n by 2 equal to m. So n equal to 2 into m. Okay. So this is rewritten as in terms of m, I have write this. So this is m will go from minus infinity to infinity. This is x of m, I can say. This is z to the power minus n instead of n. This in terms of m, this is twice m. Therefore, this is basically what this is the z transform, or this is basically x of z square. Okay. This is z square, x of z square. This is in terms of z square. Okay, like x of z, this is in terms of z square I'm getting here. Now, similarly, I can say for the L upsampler, the factor L upsampler. This we have illustrated for factor 2. So what we got here? XU of z equal to x of z square I got here. So for the factor of L, upsampler, I can write XU of Z equal to X of Z to the power L. Okay, this is Z to the power L. For 2, it is Z to the power 2. For 3, it is Z to the power 3, like this. Okay, then I can draw the spectrum for this upsampler. Okay. Now on the unit circle, now I know that Z is what? Z equal to R e to the power j omega. On unit circle means R equal to 1. So R Z equal to e to the power j omega. So the input output relation in that case, I will write like this. Okay, XU of Z, that is e to the power j omega, where R is equal to 1. This is equal to x of e to the power j omega L, I can say. Okay, instead of Z, e to the power j omega term is there. Okay, where R is equal to 1. Okay, now I can draw the spectrum of this upsampler. Okay, so the spectrum of upsampler. So I know x to the power e j omega. This is like this. Suppose this goes from this, from 0 to 2 pi. Okay. So this is basically if L equal to 2. So XU of e to the power 2j omega. So you can see the output XU e to the power j omega is for factor L equal to 2. So you can see in from period 0 to 2 pi. So if I say this is one time period, this is the spectrum in the one time period. So you can see here. So this is repeated once again. Okay, so in this time duration. So the factor of 2 sampling rate expansion, this leads to a compression of x to the power ej omega by a factor of 2. This is compressed waveform because from 0 to 2 pi, there is, you can see this part. Like if I say this is 4 pi, so this whole part is compressed in the 0 to 2 pi term. Okay, so this will be compressed by factor 2. Okay, and there will be a twofold repetition in the baseband from 0 to 2 pi. 0 to 2 pi, there will be twofold repetition. Why? Because L equal to 2 here. Our upsampler factor is L equal to 2. If it is 5, then there will be fivefold repetition. Okay, and it will compress by factor 5. Okay, now you will get extra image in the compressed version. Okay, so this process is called imaging, as we get an additional image of the input spectrum. Okay, so you can see from 0 to 2 pi, I'm getting additional image here. This is image shown with the dark. Okay, this. So this is called imaging. Okay. So the signal will be compressed in case of the upsampler. Okay. Now this is illustrated for L equal to 2. For the general case for sampling of L rate L, the expansion there will be L minus 1 additional images in the input spectrum. Okay. For the factor of L upsampling, then there will be L minus 1 additional images of the input. Additional images will be there in the input spectrum. Okay. So this is for 2, therefore 2 minus 1, 1 image is there. Okay. So the upsampler, we know that upsampler is the interpolator. Okay, increases the sampling rate. So low pass filtering of this output XU of N removes L minus 1 images and in effect fills in the zero valued samples. Okay, so basically we do the zero padding there. So we need to again use the low pass filtering process. Okay, which removes this L minus 1 images. Okay, now here you can see this is illustrated for L equal to 4. So I'm having the input spectrum like this. Now, if I do the upsampling by L equal to 4, so in this time period 0 to 1, there will be additional 3 images. Okay. So from 0 to 1, you will get waveform like this. Okay, additional 3 images will be there. Similarly, we can plot a spectrum of the downsampler. So in case of downsampler, I can write the input-output relation like this. Y of n is equal to x of m into n. Okay, so I can get y of z using z transform. So I will write n equal summation from n equal to minus infinity to infinity. This is x of m n into z to the power minus n. Now the expression, if you see on the right hand side, here you cannot directly write this expression in terms of x of z, right? Now, in this case, what we will do, we will write new sequence. So here The new sequence is defined, that is x integer of n, x int n. So this sequence is equal to x of n equal to x integer of n is equal to x of n for n equal to 0 plus minus m plus minus 2m. Otherwise, it is 0. Why this is? Because we know that in case of our downsampler, this is y of n is nothing but x of m into n. So this x of n exists only for 0 plus minus m plus minus 2m, so on. Okay. So I have defined new sequence which is x integer of n. Now I can write the z transform for this. So y of z, I can say n will go from minus infinity to infinity. This is x of m and z inverse. Now instead of this, I can write the x integer. Okay. So x integer of m into n will go from n equal to minus infinity to infinity, z of minus n. Okay. Now I will define the new variable k, which is equal to m into n, okay, and n equal to k by m. So instead of mn, write k here, and instead of n, write k by m. Okay. So this is basically, now I can represent this in terms of x of z. So here x integer, therefore this is x integer of z to the power 1 by m. Correct? This is z to the power 1 by m. This is in terms of k, and this k will go from minus infinity to plus infinity. So in this case of downsampler, now this x integer of n can be formally created, can be formally written in terms of x of n. So x integer of n, I will say this is c of n into x of n. What is c of n here? C of n equal to 1 for n equal to 0 plus minus m plus minus 2m and so on. Okay. So c of n, for convenience, I can write like this: 1 by m summation k will go from 0 to m minus 1. This is WMKN. This is Friedel factor. So what is WM? E to the power minus j 2 pi by m. In case of FFT, we have seen this factor. Okay. So C of n, I can write like this: 1 by m summation k will go from 0 to m minus 1. WMKN. Wm, where Wm is the Tweedle factor, which is equal to e to the power minus j 2 pi by m. Okay, this m is what? The downsampling factor. Okay, now this x integer of z, I have written like this. So x c of n into x of n, z to the power minus n. Okay. So x integer of n, I can write like this: c of n into x of n. So what is c of n? For convenience, I can write like this: 1 by m summation of this term. Now I can write, if I will shuffle this summation outside and this I can take inside, and this factor. This is basically what you will get DTFT here. Okay. So this is, you can say 1 by m summation goes from this, and this is x of z into Wm minus k. Okay. So the final relation I will get here like this. So why we have done the change of this sequence? So we have written the new sequence x integer instead of x, because we cannot directly apply or express this right hand side in terms of x of z. Okay, so what we got in case of downsampling, so we got the final term like this 1 by m summation k from 0 to m minus 1 x of z m wm minus k. Oh, okay. So for if I take m equal to 2, the factor 2 for downsampling, so I'm having the same input sequence here. So if I do this downsampling, so I can say the DTFT of this output, I can write like this: y of e j omega is nothing but 1 by 2 x of e j omega by 2 plus x of minus e j omega by 2. So why? Because this Wm factor is here. Okay. So this can be written like this. Okay. Now in case of downsampling, x to the power e to the minus e j omega by 2 is nothing but what? X of e j omega minus 2 pi by 2. Okay. This we can write like this: w omega minus 2 pi in terms of omega minus 2 pi. So you will see the overlap in this. This is addition of what? X of e to the power j omega by 2 and x of minus e to the power j omega by 2. Okay, so this y of this is nothing but 1 by 2 addition of this. So you will see here the aliasing effect. This is aliasing because this is overlapping in this region. Okay, now there is an aliasing effect here, the downsampler. Okay, now we cannot directly shift the signal by amount 2 pi here. Why? Because there is overlapping here. Okay, now the aliasing effect in this downsampler. So the downsampling I can write, I can show in the block diagram like this. Okay. So the plot of these two terms, that is x of e to the power j omega by 2 and x of minus e to the power j omega by 2. So here is overlapping. You will see if overlapping. So I'm having a signal like this. Okay. Only this type of signal you will get here shown in the figure. So the plot of these two terms have an overlap and hence in general the original shape of x of e j omega. What is the original shape? This is the original shape of x of e j omega. Now in the output of this downsampling, you will see this shape is lost. Okay. So when I downsample this x e j omega, the shape is lost. Downsampling shape is lost. Okay, because of aliasing effect. There is overlap. Okay. Why? Because this is because undersampling. Due to undersampling, there is aliasing effect. Okay. So there is no overlap, no aliasing if x of e j omega equal to 0 for omega greater than equal to pi by 2. Okay, so due to undersampling, this aliasing effect is there. And if I take x of e j omega equal to 0 from omega greater than equal to pi by 2, then this aliasing effect can be avoided. Okay, now y of j e j omega is basically periodic with period 2 pi. even though the stretched version of x of e j omega is periodic with period 4 pi. Okay. Stretched version means uh, in case of upsampling, there is a compression. In case of downsampling, the input sequence will stretch. Okay, so that is the stretch version is this output of the given sequence. Okay, so this is, if I stretch it with n equal to 2, then there will be a period of 4 pi. Okay. So in general case, the relation between the DTFT of the output and the input of the factor m downsample, this is given by y of e to the power j omega 1 by m, k go from 0 to m minus 1, x of e to the power j omega 2 pi k by m. Okay, this is the general relation. Now, this y e to the power j omega is sum of m uniformly shifted and stretched version of x of e to the power j omega. Y of e j omega is basically the output, uh, downsampled output of x of j omega by m, downsampling by m, okay? And it is scaled by the factor 1 by m. In general case, we can write like this. Okay. So upsampler is quite straightforward. Downsampling is little bit complicated because we are doing the change of sequence here. X, instead of xn, we are writing x integer of n. Okay. So this is the original the original given sequence. Now the aliasing effect is absent if and only if x e to the power j omega is 0 from omega greater than equal to pi by m. Okay. So in case of n equal to 2, if omega is 0 from pi by 2, then it is aliasing effect is eliminated. Okay. So if x of j omega is 0 in that case, it will be eliminated. In this case, you can see this is stretched up to pi. So if it is up to pi by 2 and the remaining points are 0, then we can eliminate this aliasing effect. Okay, so in this case, you can see the output of downsampling is like this. Okay? This is the output of downsampling. Okay, so you can differentiate between this input sequence and this input sequence. Okay. So the sampling is very important. It should not be the undersampling in that case. Okay. So there is a theorem which is Nyquist and Shannon's sampling theorem. Okay. So the Nyquist theorem concerns digital sampling of a continuous time analog waveform, and the Shannon's sampling theorem concerns the creation of continuous time analog waveform from the digital discrete samples. Okay, so this theorem is very important. Now, what Nyquist theorem says, the Nyquist theorem states that an analog signal must be sampled at least twice as fast as the bandwidth of the signal to accurately reconstruct the waveform. This is very important. This theorem is very important. The Nyquist theorem states that an analog signal must be sampled at least twice as fast as the bandwidth of the signal to accurately reconstruct the waveform. Okay. Otherwise, the high frequency content creates an aliasing effect at the frequency inside the spectrum of interest. Okay. So the aliasing is basically overlap. Okay. So the alias is a false lower frequency component that appears in the sample data acquired at too low sampling rate. Now in this figure, you can see this shows the sine waveform of 5 megahertz, and this is digitized by a 6 mega sampling per second, ms by s. 6 ms by s mega sampling per second analog to digital convert. Okay. Now in this figure, the dotted lines represent the sine waveform being digitalized, while the solid line represents the aliased signal recorded by the ADC at that sample rate. Okay. Therefore, this is very important that the analog signal, this is the given analog signal, this dotted lines. This is with the frequency 5 megahertz sine waveform. Okay. So sampling is very important if I want to digitize this. So if I use this 6 mega samples per second analog to digital converter, so at least the signal must be sampled at least twice as fast as the bandwidth of the signal. Okay, that is 5 megahertz. At least should be twice of that. Now, what is the Shannon sampling theorem says? The Shannon sampling theorem states that the digital waveform must be updated at least twice as fast as the bandwidth of the signal to be accurately generated. So that relates to the continuous to discrete conversion. Now this is related to discrete to continuous conversion. So this theorem states that the digital waveform must be updated at least twice as fast as the bandwidth of the signal to be accurately generated. Now this is the same figure which is having 5 megahertz sine waveform. Now what we are doing, we are generating this 5 megahertz sine waveform by 6 megasamples per second DAC. Okay, so this dotted line now is the desired waveform, and these arrows are the digitized samples. Okay, now what I want to create the continuous sine wave signal of 5 megahertz. Okay, now the solid lines indicates the signal that would be seen. That is the output of DAC. So this is the Shannon sampling theorem. Okay. Now, in the system where if I want to generate the accurate signal using sample data, we must set the sampling rate high enough to prevent aliasing. Okay, this is very important in case of the sampling the signal. Sampling of signal is very important. Okay, so these two theorems are important in this case. Okay, so what this theorem said, according to this theorem, the sampling rate must be at least twice the highest frequency content in the signal. Okay, it should be at least twice the higher frequency content. Then the number of samples will be closer to the original representation. Okay. So this is about the sampling theorem of sampling theorem, that is Nyquist and Shannon's sampling theorem. And if you see the application where this multirate DSP is used, so these are the applications. Okay. So this is about the multirate DSP. Okay, so mostly we have covered the theory part here. So the extended version of this multirate DSP is the next topic, that is uh, interpolator and the decimator. Okay, so there we will see the numerical problems. So this is just an introduction to that. Okay, so today we will stop here. I will provide a recorded lecture for interpolator and decimator topic. Okay, because we are not having any class next week. So I will provide you the recorded session for that topic. And after that, we will take discrete time series topic. Okay, so we will stop here today. Yes, student, any doubt is there? Are you following this
No, no.
lecture?
Yes, sir. This slide will be shared on Moodle. Okay?
Sorry, what you said? The PPT.
Slide. Yeah,
Okay, okay, I will
this
share
will
it.
be recorded.
Okay, so we will stop here today. Huh?